It's my honor to introduce Sonja, my great colleague, Sonja Wogrin. Uh, so Sonja is a full professor at Graz University of Technology. And a bit about Sonja's background. Sonja received her bachelor from Graz University of Technology. Then she moved to MIT for her master. And then he moved to Spain, to IIT Comillas. And I think you started your PhD in 2009, exactly the same time as me. So Sonja and I, we were working on almost similar topics, strategic investment for generators in two different Spanish universities using two different methods. But what I remember nicely is that in almost all conferences we met each other at Informs or journal meeting. So I remember I know Sonja from our PhD time. So then you stayed in Comillas as assistant professor and associate professor. And almost 4 or 5 years ago, you moved to Graz University of Technology for a chair position and being a full professor. Also, Sonja received ERC starting grant 2023, 3 years ago, on data aggregation of net zero power systems. And I guess we will hear about your ideas here today. And on a very important note, Sonja now is a member of Austrian Academy of Science, which is a very, very big honor. Sonja, we are very looking forward to your presentation, and thanks again for accepting our invitation. The stage is yours.
So I hope you can all hear me. Yes. Well, Jalal, thanks a lot for the really great introduction. Now you have oversold me a lot, and now the only thing that you can be is disappointed. But I'm really, really excited to be here. As Jalal just mentioned, we go way back. Let's not talk about how long it is. I'm suffering a little bit about that. But I'm really, really happy to be here. This is my first time at the summer school. I'm really happy that we could make it work. And I already got to meet a lot of you in the last couple of days and have chats, and hopefully we'll have a lot of continuous chats about this work. And I brought some treats for you. So apart from what I think is very, very cool research, I also brought Austrian chocolates for you. Yeah, you have to bribe students. I know, I have kids, so I know how it goes. So I brought this thing, which you might have seen already. It's Mannerschnitten. This is like a very, very Austrian thing. They're wafers, hazelnut wafers. They're vegan, by the way, so for those of you who are vegan, you don't have to worry about this. And I also brought some Austrian chocolate. Actually, the county where I work is Styria. And in Styria, they have a chocolate factory, which is called Zotta. And they're ecological, and it's really cool. You can visit the chocolate factory. They have like 700 samples. So whenever you come to visit me in Graz, then we can organize a visit to the chocolate factory so you can eat even more chocolate. Unfortunately, you have to earn the sweets. And you will have to earn it doing a little bit of coding later on, and I will tell you all about this. So first we'll talk about a little bit of theory, and I will hope and guide you through some of the ERC research that we have been doing. But if at any point you have any questions or criticisms or anything, really just stop me at this particular time and we have a discussion, because I think then it's easier when we have the slides to talk about this. Okay, so let's get started. Before talking about all of the detailed work, I think it's really important to also mention the people behind the work. And the people you see up there, this is the core team of the institute that I'm heading. So from left to right, you have Simon Malacek, Felix Auer, Yannick Werner, who is a postdoc at the institute and who Jalal was very nice enough to recommend to come over, so good for us. Then we have Thomas Klatzer, Benjamin Stöckel, Robert Gaugel, me, Karina Lichtenecker, who is my team assistant that I couldn't live without, she's the best. Luca Santosuoso, who also spent a little time with Jalal. This is, maybe I should be giving you the chocolates to keep sending over these really, really smart students that help a lot. Marco Kwanchnik, Marco Arnaiz, and Jakub Rybka. So those are the people behind the work that I'm presenting here as well. And I'm really, really lucky that, that they're also excited about energy and power system and optimization and modeling as I am. Down here in this picture is another initiative at the university. We have a research center that's called Energetic, which is really an interdepartmental research center where people that are interested in energy and sustainable solutions for energy future work together. So it's not just the electrical engineers that talk to each other, but it's really mathematicians, architects, social scientists. And if you want to have a sustainable energy transition, as Jenny has just told us, you need more than just the technical perspective to get this done. So what's on the menu for the first half of my talk today? We're going to start a little bit to talk about data aggregation for optimization models and why this is important, and the different dimensions of complexity that could lead to computationally intractable problems. And then we will go further and say, okay, can we make all of the methods that we're going to develop work if we have network constraints? What if we have time linking constraint like cramping? What about storage? We will talk about error bounds for time series aggregation. If all of this doesn't make any sense to you yet, don't worry at all. I will tell you all about this. And then we will also talk a little bit about spatial aggregation, so reducing grids. And that will be the first half, and then you will get some sweets from me for being such good sports. Right, so power systems, energy systems are very complex. Actually, for me, the fact that the power system works the way it does is like almost a miracle. It's an engineering miracle. The fact that we have intermittent renewables and we're trying to change a power system that has been traditionally thermal-based to something that is decentralized and highly renewable. So we're trying to take our Fiat and build it into a Ferrari, but while we're going at 200 kilometers per hour on the freeway. Don't say that the Ferraris will catch fire or anything like this. You're not allowed to talk bad about Ferrari because my brother-in-law, he works there, and so Forza Ferrari, let's hope they win a world championship. You can dream. So this is getting so much more complicated, and I've brought a couple of pictures here to show you the amount of renewable energy sources that we have been getting into our power systems. And we have to be honest, renewable energy sources are great, but they also come at a high price because there are more challenges. Because it was a lot easier to just say, burn more gas on, and that was that, instead of like having to do demand side management and check, you know, have we stored enough renewable energy to be able to use it later. So I think this is a really, really exciting place to be working. I think all of you made the right choices in life to be here and work in this really, really interesting field. And I think that you will be super happy and entertained for the upcoming decades. So it's not going to get boring, for sure. Now, when we talk about something like generation expansion planning, so deciding how many generating assets you're going to need in future power systems. Lena yesterday was telling the policy goals that we have to 2030, 2040, 2050, how many new power plants do we have to build, when and where. Then from a mathematical perspective, you could cast this as a very simple optimization problem that you have up there. And I don't want you to get lost in the details of the nomenclature. So essentially, this is just we're meeting demand at a particular time t. So this is our demand balance that we have here. We have power generation. Power generation has to meet demand, and we have some constraints here. You cannot generate if you haven't built the power plant, right? So X here is the investment decision, and this is up in the objective function. And depending on how many technical details you put into your model and whether it's discrete or not, these models become very, very challenging to solve. And they're actually NP-hard. So these mixed integer formulations, they can be NP-hard. So these are computationally very, very tough problems. And for me, there are multiple reasons or multiple dimensions why these problems are so hard. And many of you have mentioned them over the last couple of days. So let me just talk about the reasons or the dimensions that I think lead to intractable problems, especially in energy system planning. First of all, you have an uncertainty dimension. And uncertainty really stems from a lot of different sources. First of all, you have intermittency. So you don't know, is it going to be cloudy tomorrow or not? And that's going to affect solar irradiation and the power generation from PV panels that we can have. But you also have policy uncertainty. What are governments going to decide? What are they going to implement? What are certain oligarchs going to do in the future? How are you going to put this into your model? This is all uncertainty, and there are very, very different sources of uncertainty. So if you translate this down into optimization problems, then this could lead to a different set of scenarios. And we have heard about different weather years that you might be taking into account. Jenny has also mentioned this because they were looking at historical weather years and future forecasts for weather realizations. And this makes your model bigger. The more scenarios you have, the bigger the model. What could you do there? You could do scenario reduction, for example, or a couple of other things. But this is one of the sources of computational complexity of your model. Then you have a technical dimension. And what I mean by technical dimension is, and this is especially true for power systems are very, very tricky problems. So you have underlying technical constraints like power flows. The AC optimal power flow is a non-convex problem, but this is the reality of electricity systems, right? You also have investment decisions or unit commitment decisions. So if you start up a unit, this is a discrete decision. So this is going to mean binary or integer variables in your model, and that makes your model a lot more difficult than if it was just a continuous problem, right? So you have this on-off, do I invest, do I not invest kind of decision. And this is really important for power systems because you cannot just say, well, build half a unit or turn on half a power plant and we'll be fine. In operation, we're not, right? So these things are important to consider. And what could you do there, depending on whether you have non-convexities in terms of the AC optimal power flow, or you have discrete variables in your model. You could do decompositions, for example, in order to solve them numerically, or you could try and come up with better mathematical formulations, convexifications of linearizations of your actual problem. And this is also very difficult. And then third dimension for me is the grid. So we have a spatial dimension here, and depending on the problem that you're looking at, you have an underlying power grid. So if you think about planning for Europe 2040, 2050, you have to think about not only how much generating capacity do we need, but where do we put it, and how is this going to affect underlying power flows. So you also have a grid that is making things more complicated. And in order to solve that, you could, for example, aggregate the grid or make simplifications, run a single node first, not run an AC OPF, but maybe run a transport problem. There are a lot of different tools that we have in our toolbox. And then last but not least, I want to talk about the temporal dimension. Because if you maybe look at stability analysis of your power system in a one-shot kind of moment, that's one thing. But if you're looking at an investment problem and you're looking several years or several decades into the future, then maybe you want to have 8,760 hours of the year in your model that you are going to evaluate. And every number of variables that you have in your models for every generator and every line in your power grid that you multiply with 8,760 is going to blow up a lot the size of your model. So this is kind of the curse of dimensionality that you have there. And what you could do to fix this is time series aggregation. And I'm going to be talking about this and a couple of other things. And this is just a little bit of pictures of different people at the Institute who work at different topics there. And you will hear about this spatial aggregation and time series aggregation things in more detail now. Okay, so what is time series aggregation? A lot of you have already been using it and are more advanced, but for those of you who have never heard of this before, I just wanted to make a very simple definition of all of this. So imagine you have a certain time series of data, right? So this could be your system demand. This would be a time series of demand over time. You see the magical number of 8,760 hours per year, where you have demand that you have to meet. And another time series that you might have could be wind production, solar PV production, or capacity factors of those. And those time series might be inputs to your energy system model, to your power system model. Now, as we've already talked about, like this problem of having to multiply everything in our model with 8,760, which is a big number, we're trying to condense, to compress this dimensionality. And this is what time series aggregation is, right? So time series aggregation takes this data, and then it compresses it in order to have a set with a much smaller dimensionality. And in the past, this might have looked like this. So you have a load duration curve here that you could get taking this time series, ordering it in a monotonically decreasing way, which leads to the continuous curve here, and then cutting out a step function that follows this load very nicely. And then here you would have, let's see, 1, 2, 3, 4, 5, 6, 7 representative periods that have a value for the average demand, and they have a duration. So how many hours do I have for this average demand? And then you have reduced your 8,760 hours to 7 values, right? The integral over both curves is the same, so the amount of demand that you have in your overall system is the same, but your model you would just have to build for 7 representative hours in this case, so that's much smaller. Another option that you could have is what you see here, so representative days, or as Jenny has mentioned it, representative weeks. So they use 12 representative weeks in their model. It could be days, it could be weeks, so this is a little bit different from this here, because here you actually have a 24-hour vector of a chronological time series. If it's a week, then it's 168. Depending on what the application for your model is, you may pick a different one. And then you pick representative days instead of hours. And there is a lot of literature there on how to do this, how to pick representative days or hours or whatever. But most of this literature, they focus on approximating the input data well. So when you compress your data to representative days, for example, they're looking for the representative days that best represent the original time series. And you're going to say, like, that makes total sense. And it does, but it depends a lot on what are you going to use this compressed data for. If you're going to use this compressed data to, like, just analyze the actual data that you have, or have a probability distribution of how many times happens what, some statistical features of your data, that's totally fine. But if you're going to plug this aggregated data into an optimization model later, then you have to be very careful, because really then you don't care about approximating the data, you care about approximating the full model output well. So you want to pick representative periods that best approximate full model outputs, not the data. And I'm going to show you an example where you really see very pragmatically how different you could pick the representative periods then, and the difference it makes to account for the model outputs in your data aggregation. Another thing that these methods that focus on the data, which are sometimes called a priori methods as well, they don't give you any error bounds on how good your aggregated model is going to be. Right? So you don't have any control on how good this is. And you might say, well, you know, we just do the best we can, and this is fine. But if you think about rebuilding an energy system for 2050, then we're talking about a lot of money that we're going to invest in infrastructure. And power systems and energy systems are very expensive. So if you run a model, your favorite European energy system model, for example, PIPSA, which is very famous, and you run this on representative days, it would be kind of nice to know, are you 5% off the social optimum, or are you like 50% off? Because 50% is a big number, right? And the thing is, a lot of times you just don't know. Right, so this brings us to a computational challenge. So we have very large models. Our European power system digital twin, if I ran this for a year in hourly resolution, it would have around 660 million variables. If you ran this on the Frontier supercomputer, then this would probably take one model run 18 days. And unfortunately, on my workstation, it doesn't run. I don't have the Frontier supercomputer in my pocket. But I'm just putting this here to make a point, right? So the point that I'm trying to make, and this is what we're working on in my ERC project, is if we can compress data smartly, then maybe we can reduce this 660 million to 0.5 million, and the outputs are still going to be very good or the same. And if you run this model, then I don't need the supercomputer, I can just do it on my regular workstation. And this is one of the goals that we're having, that really everybody can do European power system analysis on their computers or on their local server infrastructure. Okay, so now a couple of, an example, just as a proof of concept. So I'm going to start off with an economic dispatch problem, where your index G are the generators and your index K are the time steps, so the hours of the year if you want, right? So what I'm doing here is I'm minimizing overall system cost. I have power generation, P, for every generator in every hour. I have variable cost here. Uppercase letters are data, lowercase letters are variables. I have a cost for non-supplied power in case this would happen. A very simple demand balance where I have demand at each hour. So this is one of my time series input data. I have to meet the demand, and I have upper and lower bounds on my generation. And I have snuck my capacity factor into my upper bound here. So this upper bound of installed capacity, you see here it depends on K, because it's the installed capacity times a capacity factor that I'm multiplying this with. If this is a thermal generator, a gas-fired power plant, then this capacity factor is always 1. And if it's wind or solar PV, then you have something that's between 0 and 1, depending on the time of the day. Okay? So if you do an aggregated model instead, so here, instead of having 8,760 Ks, you just have a couple of representative periods that here I'm going to call R, and they are supposed to be a lot less than 8,760. And then the model looks almost exactly the same, just a couple of small differences here. So where it said dk, here now it says dr. So this is your representative demand in representative period R. If you think back to the load period, this was your step function. Then here you have a weight, so how many hours belong to this representative period. And you also have to take some averages over these capacity factors. So for these representative hours, you also have an average capacity factor. Very simple. So if we have a simple problem where we have 2 generators, one thermal and one wind generator, and we built this model for the entire year with hourly resolution, then this gives us 26,000 variables. This is a toy problem, right? Yeah, just to make a point. If instead of having 8,760 time periods, you just pick 3 representative hours to represent the year, then you get a model that's only 9 variables. 9 is a lot smaller than 26,000, right? So how do I pick these 3 hours in this case? You run your favorite clustering algorithm. So I pick k-means. And by the way, every x here, every small x, is one pair of demand and capacity factor data. So there should be 8,760 small x's on this plot. I give this to k-means and I say, give me back 3 representative hours. And then these large x's are the centroids of the cluster that k-means gives me. I built the model with these 3 representative hours, and it's really bad, you guys. It's really shitty. I get an error in the objective function value of 90%, and I get an error in loss of load of 100%. So I don't capture loss of load at all. Who thinks this is surprising? Okay, very good. Who thinks it's not surprising? Can anybody tell me why this is not surprising? Would anybody be brave enough to talk to me in the morning? Why is this? Yes? Yes, so I'm going to repeat, we're not accounting for the demand shape, we're not accounting for when generators are generating, we're just looking at the data. But this is what a lot of us do or have done in the past, right? So 3 hours is not a lot of hours to approximate all of the different states that the system could be in, right? Wrong. So if you did this differently, and you clustered in the way that I'm proposing here on the right-hand side, which is exactly doing what you have been mentioning, which is looking at what state is the system in, and in particular here, I'm looking at who's the marginal generator of the system, right? You could also, instead of saying who's the marginal generator, you could look at this from a different perspective if you're more from a math background. So you could think of what is the optimal simplex basis if you're a simplex fan and you have done a lot of simplex tableaus in your life. Or you could think of what are the active constraint sets in different hours, right? So the active constraint sets, they characterize the same thing. What is the state the system is in? And if you do it this way, and you then take the centroids of the blue, black, and red areas, you get a model with 3 representative hours, and this model has 0 error in the outputs of the model. And so this means that with 9 variables, you have captured perfectly what this system is doing on average. And the reason this works is because this was, of course, a linear program. So in linear programs, you have simplex theory, and then you can actually prove mathematically that this is right. But this is a very nice example to show that the hours that best approximate the data are not the hours that best approximate the model output. Because these here are the hours that best approximate the data, if you just pick 3. And they give you 90% error in the objective function value, and you don't capture loss of load at all. But if you pick them this other way, with 3 hours, you can get it perfectly right. And you can also see why, for example, you get this loss of load, because this centroid here is a little bit to the left, so it falls in the black area. And this means that if your average, your representative hour, your representative day, does not fall in the active constraint set where you have loss of load, you're not going to see it in your aggregated model. And that's a problem, because then you expect your system is going to behave better than it actually might in the future. So this proof of concept idea is in this paper, if you want to check it out. And of course, this is a very simple problem. But this is where it all started, where we said, okay, well, actually, maybe we should look at whether we can make this work for more complicated models. So with this, the questions that we want to be looking at is, can we extend this to network constraints? Can we extend this if we have time linking constraints like ramping or storage in your model? Can we still get exact time series aggregation then? And are there any performance bounds that we can prove on this type of aggregation? Okay. So this brings us to part 2, where we talk about the network and ramping constraints. So here, I don't want you to get lost in all of the equations. That's not so important. The thing that I want you to focus on is that we had this economic dispatch, and now we're introducing a grid. We're introducing simple network constraints. So now, on top of everything, we have buses, I and J. And we have in the power balance, you get flow, right? F is flow at time step k from node j to node I. So this is incoming flow, outgoing flow, and you have upper and lower bounds on your flow because you have transmission constraints, right? So if you introduce this in your network, do you still get this behavior of these active constraint sets? And actually, you do. So in this plot, you have your 8,760 points of your original time series, and they are colored in the way of what your active constraint set is, right? So here in this particular case, we have 5. And you see there are some very crisp separations of these, like there are some vertical and horizontal lines that go through. And these vertical and horizontal lines, they represent transmission constraints being activated or not, so lines being congested. So if you didn't have this particular line, then the orange and the green active constraint set would be the same. You would have the same marginal operator, the same behavior, but you have a line congestion, so then this active constraint set switches. And if you approximate this with just 5 representative hours, you again get it perfectly right. Okay, so in this particular problem, you can get rid of almost all of the hours. You just need 5 representative hours that are represented by these black dots here in order for your aggregated model to give you the perfect model output on average.
Are you still using simplex to identify active constraints, or no, you solve problem for each hour separately?
So in this, the simplex thing still works here, but because the network doesn't depend on time. So essentially, it doesn't change anything at all in improving it. The tricky question, which of course Jalal knows because he's very smart, so he spoiled the question is like, how do you come up with these active constraint sets beforehand? But I will get to this a little bit later. Okay, so in this particular case here, just to show, if you knew these active constraint sets perfectly, then you could solve the system with your aggregated model perfectly. Actually, you wouldn't even have to solve it anymore. You would just have to solve, on average, these 5 hours once, and you have a solution for this, and then every future instance of your model, you don't have to solve anymore. You already have the solution, because if you know how the data corresponds to the active constraint sets, then you're done. You have a question? Yes. You mean if we like do a relaxed, if we relax integrality? So I think it really depends exactly on the particular problem that you're looking at. If you're looking at investment problems, maybe from a European perspective, if you like build this one power plant more or less, you wouldn't mind so much. But if you're a grid operator, you would mind a lot, like building the line or not building the line. And locally, it could have a big impact on power flows. And so maybe like from a European perspective, it might not be that much, but regionally, depending on what you're using your analysis for, it might change a lot, because a lot of people, I mean, would solve pipes for Europe, but they would only really care about what happens in Austria, right? So we solve pipes for Europe because we're not an island in Austria. And then you solve it, but kind of just to see what is the flow across cross-border transmission lines, and then see, okay, what does this mean in Austria? How much do we invest here? And there, then you really care about one more or one less. There, it's not so. So it really depends. Depending on the problem that you're looking at, it really depends. I mean, of course, if we're going to say 2050, you could also say nothing really matters, because nobody knows. Nobody has the crystal ball, and like the uncertainty introduced by policymakers might be a lot bigger than the impact that time series aggregation can have for you. But we have to like keep our mental health to see that there is something that we can do that we have an impact on. So if you if you can get more bang for your buck, essentially, use the same amount of representative periods but make them tighter, then why not do it, right? So, and also I'm a mathematician, so I think this is really fun. As for the motivation for this. Okay, so as I just mentioned, this the proofs and the simplex theory, this extends to the grid very nicely because in the end the grid doesn't depend on time. But what about constraints that do depend on time, for example, ramping? So if you just focus on these constraints here, they are very simple ramping constraints. So if you have a thermal power plant, then the delta in power output that you can get from this thermal power plant should not be infinite because they have physical limitations. So for example, a gas or a coal-fired power plant is not going to ramp up from 0 to 500 megawatts in 1 hour. You have to start up, and then you have to heat up the steam, and if the steam doesn't have the right heat, then there are still some tiny water drops in the steam, and if these tiny water drops hit the turbine, then they shrapnel the turbine and it breaks. So this takes a little bit of time, and this translates into, in a very simplified way, this ramping constraint that relates the previous hour, k minus 1, to the current hour, k, and it limits this delta by a constant, a ramp-up constraint. So from 1 hour to the next, your power plant can do at most a delta of 50 megawatt, for example. This makes time series aggregation more difficult because now constraints depend on consecutive time periods. You cannot separate them anymore. And this is something that I did before, because in all of the plots before, I didn't really think about chronology between, I just assumed, I also didn't have constraints that linked these time periods together, but now I do. And if you think about what the system matrix of your optimization problem would look like if you introduce these constraints, then here you have this system matrix, right? These are your coefficients. Then here are your variables. This is your data in a very simplified way. And everything up until this point here did not link variables of different time periods. So if the first 2 columns corresponded to the first time step and then the second time step and the third, then actually if it wasn't for the last 2 lines of this coefficient matrix, I could have sliced up this matrix into different independent problems because they were not related. But now I have this here, and especially here you see the variable at time step 1 and the variable at time step 2, they are related in this ramping constraint, marked by these red dots. And that's a problem because now I cannot slice this anymore. But what if I knew, or I could guess, if this constraint was going to be active in this particular time period or not? If this constraint is not active in this time period, I could scratch this line from my system matrix, and then I could decompose the problem. And this was one of the ideas that David Cardona Vázquez, who finished his PhD last year, worked on. So if we could identify when ramping constraints are going to be active, then you could take the time horizon and kind of like slash up the larger model into separable independent parts. You could solve them independently. You can parallelize them. You have your submodels that you are solving in parallel. Then you aggregate all of these separate results together, and then you can compare this to your full model results. So this is what we did. And we did this for an example of the Austrian power system. Let me just check how badly I'm doing on time. Oh yeah, I'm doing really badly. Okay, but it was expected, you know. So this is Austria. Austria has 9 federal states, and this was a problem that we were looking at to see if we could make this work. How do we know when ramping constraints are active? We use ML here. So with some historic model runs, historic data, we could train a classifier to tell us, is ramping going to be active or not? Yes or no? So if ramping is active, then those are time periods that we're not going to be able to separate from each other in the model. But as soon as there is some time where we think this is not going to be active, we can completely cut the model at this point, and then we can parallelize it. So the classifier had an accuracy of 92%, which already I thought was pretty nice. But that doesn't really matter so much. What matters is when you look at the aggregated model outputs, how much does this error here translate into model outputs? And in the problem that we had, actually the error almost vanishes. So in the relative error in total system cost was 0.004%, so very, very small. And this is an example of the error that we had of production per technology in federal state. And you see that the numbers are super small. So we have like less than 1% error in all of them, except for one in the Tyrol, which is very nice for skiing, if you like skiing. But the absolute number here, this was a very small number in absolute terms. So this relative error, even though it looks big, it's not a big issue. We did some sensitivity analysis on this, and this seemed to work very nicely. And in terms of computational time, we got 300 times speed up because of parallelization, essentially. So our full model, which was still relatively small, was 115 seconds, and the largest submodel was 0.4 seconds. So this idea of sizing up the model and being able to parallelize helps a lot. Okay, so essentially you could extend this idea to time linking and ramping and network constraints. But what about storage? So we started with ramping because we thought you have to crawl before you run. And storage is very complicated because storage doesn't just link 2 or 3 hours together, it might link a lot of hours together. And in terms of underlying mathematics, it's also a little bit different because a ramping constraint is an inequality constraint. But a storage, the storage problem that we're going to have, where we have time coupling, is an equality constraint, your state of charge constraint, which I'm going to show you now. So how do we address this? Again, storage formulation. Don't get stuck on all of the numbers, they're not important. We just zoom into this, the one equation to rule them all. Everybody who has worked with storage has seen this in one shape or form. So essentially it's energy stored at time step r is energy stored at time step r minus 1 plus what you charged minus what you discharged with efficiencies and so on and so forth, right? But the time linking happens here, and this is an equality constraint. So if we go again to our coefficient matrix and see what happens there, then you will see the problem with the time linking are these red ones here, because this is what keeps us from disaggregating this. And the idea that we had at this point there was like, what if we could guess if the storage is empty? Because if the storage is empty, then these two ones are going to be multiplied with 0, and then everything disaggregates again. So the idea was here again to do this for parallelization. As an example here, you can see a 48-hour sequence of a state of charge. And in this egg color here, we have what we call active constraint set 1, where the state of charge of the battery is going to be 0. So in these time steps, we could actually cut the temporal index and then make a submodel that's completely independent. But you can do more. The other colors that you see here correspond to different active constraint sets of your system. So this could be storage is charging at maximum capacity, it's charging again, now it is at maximum capacity. So you have different active constraint sets, and what we have seen is that if you aggregate consecutive time periods that have the same active constraint sets, you also make 0 error in your aggregated model. So what this translates to is, first of all, you can cut when you think storage is going to be 0. So now you have 2 independent submodels. And you can compress consecutive hours where the same thing is going to happen to your system. So here, instead of having a model that goes from 5 to 23, you just need 7 time steps to approximate this perfectly. And then we tried this out on a larger case study. This is actually work with Thomas Glatzer, who is an assistant professor at the Institute, and this was accepted at PSCC. So if you're going, please make sure you check out Thomas and talk to him about this work. So of course, this also helps with computational tractability. Yes, yes. Yes, so it's not just about the storage, it's also about what happens in the rest of the system. Because mathematically speaking, if storage is charging, but your marginal operator is wind, it's a different active constraint set than if your marginal operator was PV, for example. You can also merge these hours. There you're going to have an error. Because if you merge different active constraint sets, then you will have an error. But the error might be small because your marginal cost difference between wind and PV might be small. So this also gives you some information how you can do informed aggregation, informed time series aggregation. But if you don't touch the active constraint sets, then you have an exact aggregation, actually. Yeah, that's a different active constraint set because an upper bound is active or not. It might not matter so much for aggregation. It's just a different active constraint set. We have seen that many times in the model that you wouldn't charge at full capacity because maybe you don't have enough wind in the system because maximum. So you have a maximum charging capacity for your battery, but if you have less wind available, then you can charge. Then you don't charge it at full capacity. I don't know if that's what you meant, or you meant the energy capacity of the storage. Oh yeah, so maybe I should say, I mean, this is a cost minimization model, right? This is a total system cost minimization, and there, if the renewables are not available, then you wouldn't charge at full capacity. Good. So, since I'm already over time and we have to make a break at 10:45, and I still want to do other things, I will just briefly talk about how you can also get error bounds back into time series aggregation. And this is work mainly together with Luca Santosuoso. So you know about this, and Jalal has nicely spoiled, but how do you come up with these active constraint sets beforehand, right? So we don't really know this before. And we don't have any error bounds between the full and the aggregated model, and we would really like to have that. So then Luca had the very nice idea to prove that if you build your aggregated model in a correct way, you can actually prove that your model is a lower bound to your full model. And of course, you can check out the paper and talk to Luca, who will also be at PSCC. But the idea is very simple. If this is your full model and your active your constraint set, if you relax this problem, then you're going to get a lower bound. And this is what we can prove in this paper, that our aggregated model is a relaxation of the full-scale model, and that therefore it's going to give us a lower bound of the truth. And that's nice, right? So we know if we aggregate our model, then we get a lower bound of the truth. And in the ISGT paper here, there was no storage yet, but since then, Luca has already managed to prove this, including storage as well. So even if you have storage in your model, you can still prove that your aggregated model is a lower bound. And then, again, don't go into the details of the algorithm. I just put them there for you to know that this was not so easy. But the idea is you get a lower bound, and then in a projection step, you can get an upper bound, right? So for example, if this is an investment problem, you can fix the investment, run the operational problem, and then this is going to give you an upper bound. And then you get an optimality gap of your aggregation. So then here, you can increase the number of clusters if you want. And in every step, you're going to know how far away you are from the true optimal solution. And this is very nice, because this is bringing something back into time series aggregation that wasn't so specifically there, that you can actually prove how far away you're going to be from the full thing without having to ever solve the full-scale model. Right, so you get this upper and lower bound. The results, again, for the I'm not going to go through the details here. It works. Please read the paper and reach out to me or to Luca later on. You get faster computational performance here. But what I want to take a little bit of time as well is this idea of what are we clustering for? And this was kind of a philosophical question and philosophical discussion that actually started with Luca. Because Luca was like the objective function value and the optimality gap, and I was like, yeah, but what are you clustering for? What are you using the model for? Are you the system planner who really cares about what is the system going to cost? Or are you a generation company that would actually like to know how much wind investment should I build? And those are two very different settings, because in one, I might care about the objective function value, but in the other, I might not give a rat's ass about what society pays. I would just interested in like how much I should invest in. And if you, for example, care about the investment or a particular other variable, then it would be really nice to be able to get these error bounds from the objective function and use them to get some bounds on your variable outputs. But this is very hard. And so what we have come up with, or what Luca has come up with here in the idea, is to say, okay, we take these error bounds from the objective function, and we're trying to use them to get some bounds on our metric of interest, which might be the investment in wind, for example, that we care about. So then what we suggested here was to say, okay, since we already have a bound on the objective function, we can make the feasible region of the full-scale model smaller by saying, hey, you know what? The objective function has to be between these bounds. And now tell me what is the maximum and the minimum wind investment that I should possibly have to get a range of where my optimal investment is going to be, for example. How well this works is, of course, case dependent. So there are cases where this actually works nicely. There are cases where, of course, your range is from 0 to infinity, so it doesn't give you more information. But this is a first step in this direction. Okay, I'm going to skip this as well. So key messages in terms of time series aggregation here was energy system models are difficult, you guys. They are very, very fast. They become intractable. And then you have to do something, and time series aggregation is one of the many things that you could do to address this. We have answered our questions with this particular a posteriori time series aggregation method that we have developed there, where you get more bang for your buck. So you can get better accuracy for your models if you pick your representative periods right, and right means that they approximate the model outputs better. This can be exact if you know exactly what you're doing, if you don't know the structure of your model exactly, but you can use ML to kind of get a guess what your active constraint sets might look like, even if you don't know the exact truth. And you can get some performance bounds on this as well, which wasn't there before. So this is kind of, in a nutshell, the fun that we've been having with time series aggregation in the last couple of years. And now I want to take the last minutes to do something with you on a different topic. So this is not aggregating time, this is aggregating space, so aggregating buses. And there I want to give a shout out to Benjamin, Marco, and Yannick, or as I lovingly refer to them, the NPEP boys, because they have developed a Python package on network partitioning and aggregation. So this is where NPEP comes from, NPAP. And I have asked them before if I can call them NPEP boys, actually. I'm not just saying this, it was between NPEP boys and NPEPers, and they like NPEP boys more. So this is the QR code to the GitHub repository if you want to check it out. So one of the things that we have seen is, of course, in time series aggregation, you have tsum, which is a very good package that maybe a lot of you guys have been using in the past. But for spatial aggregation, we didn't really find anything that was equivalent to that. So that's why we decided to make one. And the motivation for us comes from power systems. The package is written in a generic way so that you could apply it to any other kind of grid structure. It doesn't have to be a power system. You can really apply it to anything where you have nodes and links between the nodes. But our motivation comes from the power system. And there we particularly made a differentiation between what is a partition, that's a Beyonce song, and what's aggregation, and separate the two. Because for us, partitioning is you have the full-scale grid, and then you put individual nodes into clusters. That's a partition, right? So every node is assigned to a particular cluster. And then the aggregation part would be, so how do you merge what you have put into separate clusters? And that depends a lot on what you're going to do. Because if you have a transport problem and you have different lines that goes between different clusters, you might just sum maximum capacity and that's that. But what if you're actually running a power flow? What if you have a DC-OPF? What if you have reactances? What do you do with those? You can't just sum the reactances and say, oh yeah, that's going to work out. You need to do something else. And since the guys started doing this by hand and they were super frustrated because they had to do it so much, they coded the package so that other people wouldn't have to suffer like they did. So the option that you have here, so you have several strategies to partition. You have several strategies for aggregation, depending on whether you want this to be a transport problem, or you have parallel reactances, or you want to do cron reduction and these kind of things. And in the partitioning, you can either look at geographical distances between buses, you can look at electrical distance, or you can include some additional information that you have about your system, which could be LMPs, if you have this from past model runs, or any other information that you have for your specific system. And then they also gave the option of doing a voltage-aware aggregation, and I will come to this in just a couple of seconds, and they're able to detect AC islands within your grid. So this is an example of how the package works on PipeSA data, actually. Right now, Yannick is in Berlin working with Fabian Neumann to integrate this package into PipeSA as well, because they do their own spatial aggregation. And so we have done a pull request so we can actually integrate the package into that for this to be more useful to people. And here you can see the different steps of the original grid, and then what the grid looks like after you have partitioned it. So here then every color of a node tells you to which cluster it belongs. And then in the aggregation step, then you have the final part where you actually have then aggregated lines and aggregated buses. Why does voltage awareness matter? So since Benjamin is doing his PhD in spatial aggregation, and he's an electrical engineer looking at grids, for him it matters if you need a transformer or not. So if you have a grid and grid data like the PipeSA data does, for example, where you have several different voltage levels, if you aggregate and you ignore voltage levels, then things like this could happen, where, for example, here, the green is a 380 kV part of the grid, and then the orange one is the 220. And if you aggregate without separating those, then you might lose the congestion that you had in the real grid. So here, the X's represent grid congestion that you might have had. And if you account for the voltages that you have, then actually your aggregated grid would look different, and here you would maintain the congestion in your grid. So this might be something that if you're working a lot with electric power grids, this might be useful to you. Yes? Yes. So it's partitioning first and then aggregate. You first need to know which buses do you want to put together, and then you decide how you're going to want to handle those. If you then, for example, want to put an average, or do you want to put a medoid or a centroid? Do you want to sum? Do you want to calculate an equivalent reactance or not? Yes, yes. So once you have partitioned, then you have your group, and then you decide how you aggregate that. But you need to know how you want to partition before you aggregate. Yeah. Okay, so this is an example of a difference of like geographical and electrical distance aggregation. And now we have 10 more minutes before coffee. So what I would ask you to do is scan this, and this should bring you to a Colab workbook. The link for the Colab workbook is down there. If the scan doesn't work, I'm not sure if it works with the resolution of the beamer. You will let me know if you end up at a Colab workbook or not. It works? Yes. Ah, great. Okay. So this Colab workbook, before you start to do anything, please create a copy of this in your own Google Drive. So if you go to File, Save Copy in Drive, then you have your own copy of this Colab notebook that you can play with or alter in any way that you want. Do you need the QR code again? Yes. I saw. Back from coffee break, I hope you enjoyed the cookies. So now we hopefully managed to figure out that everybody who has a link should be able to have access to this. Then you can create this copy that I already did. So you just go to File and then Copy into your drive. So you have a copy of the Colab notebook. And then I already hit the Run All button so that then I don't have to wait so long to tell you about this. You can do the same. If you hit the Run All button, then it will load the package and it will generate the pictures, so you get a couple of images here. So let me see, we have until 12:30. Okay, good. Right, so my idea for this here was really just to show you a little bit of the different functionalities of the package, and that you have some Colab notebook available that you can use and you can play with when you have more time. If you have any spatial aggregation needs, then this might be something that you could refer to. Okay, so this is the NPAP package here. We loaded the package, and we also are going to load the PIPESA data. So just so you know that we're also going to load the PIPESA data. Here is a little bit of more information about the architecture of the package itself. This is what our software developer Marco did. If you're interested, yes. But if you're more interested in the electric power engineering part, then we will move on a little bit more. Okay, so this is the facade manager. Here in 2.2 we load the data. And then this is the first time that we actually plot the figures. So this is the PIPESA data set that we got here, which has a lot of buses actually. And something that Benjamin also saw when working with this data was that there were some parallel edges, so parallel lines that were in the data set because they might be in the real power system. But for the sake of the aggregation here, we got rid of those. So in this 2.3 pre-processing step, we got rid of these parallel lines, so now we only have around 8,000 power lines in between here instead of the 9,000 that were there before. And then in 2.4, this is the first part where we're actually doing the partitioning. So here, there are a lot of different options. There is a very nice online documentation that the NPEP boys did. So there is this partitioning guide if you want to check this out and read a little bit more about the different ways that that you can partition in here and what are the different command words for this. And the first thing that we're going to do here is we're going to do to aggregate this grid into 200 clusters. So we are going to have 200 aggregated buses. Oh, no, okay, I thought there was a question. And we're going to do a k-medoids clustering. There are 13 different algorithms that you can pick from if you don't like k-medoids, if you prefer k-means or hierarchical clustering, for example, then you can also do this. And you will see down there later on that this is quite easy. So here you really just have to change the command of how you want to cluster. And then, as we have said before, so we have made this separation between partitioning and aggregating. So this is the first partitioning result. So here you have 200 different clusters, which are indicated by the color scheme on the right. So here, these colors mean different clusters. So the green are different clusters than the blue ones. And all of the buses that have the same color here, they belong to the same cluster. So for example, if you want to look into Madrid, which is where I used to live for a long time, so there are a lot of yellow buses up there which have been put into the same cluster and that are then going to be aggregated later on. Okay. So in aggregation, just for you to have a little bit more information, if in your research you have problems with or you work with spatial aggregation, then please read this in more detail or reach out to me or to one of the collaborators, and then we can talk about this in more detail. There are different options that you can, and different strategies in your aggregation that you can do. So there are some domain-specific things. For example, what do you do with line reactances, which is something that is very specific to electric power grids, but which might not be relevant if you have a hydro grid that hydro pipes that you're modeling. And then you also have the option of providing properties of how you want to aggregate certain things. So do you want the aggregation to happen via a sum, or do you want to calculate an average, or do you want to calculate, for example, an equivalent reactance? If you have several lines that goes from one cluster to another, then how do you want to treat this in the aggregation? And this is something that you can specify. So here, as an example, you can see if I'm aggregating the latitude, then what I would want to have in my aggregation is the average value of all of the latitudes of all of the buses that I have aggregated. Okay, and then you can visualize this in here. This is a small visualization of the 200 bus network that you have created. And now this is in section 3. This is something about this voltage awareness. So maybe if I think you mentioned like a master's student or something who was like looking at this. So maybe this is then more interesting for him to see that there is a difference between like simple aggregation where everything is uniform and some things that are just electric power specific, where you can really make a differentiation between your different voltage levels. So if now here, for example, we look at the same pipe-saw grid, here you can actually also visualize, for example, if you have DC links. So the pink lines there would be DC links. And this is something that we have done because when we did aggregation, an aggregation of the pipe-saw model, for example, our spatial aggregation would just put everything together, even though this would happen in different AC islands of the European grid. And then you might wonder, does it make so much sense that there are like buses from Sweden and Denmark then actually being put together in this model? Because what we use it for is power systems model later on, right? Okay, and then here we do another step of the aggregation, but this time respecting voltage levels and our DC islands, and then this is going to look like this. So this is a little bit different than from what we had before, and depending on your application, you might want to do one or the other. So this is just for you to check it out. Right, and then down here where it says available partitioning methods, there if you then want to play around later on and try it out, these are a couple of examples of different things that you could do, right? So you could look at geographical distance, use k-means or k-medoids and Euclidean distance, hierarchical clustering, voltage awareness, yes or no. So this is just a listing of some examples. If you want more detail, I would suggest you go to the online manual and documentation and look at this there in a more peaceful setting. And then, for example, if you wanted to try out this later on here to see, do I need 500 buses? Do I need 200? Do I need 300? Do I want this to be voltage aware or not? Then you can essentially, like just in this line, change this to whatever you might want to use, and then get results that you could plug into your optimization model. So in here, what I've brought in this package is not linked to an optimization model, but like with TSUM, the outputs that you get, you can plug into your optimization model very, very easily. Okay, and then the last thing that I would ask you to do, for this at least, is there is a very quick survey down there, which is essentially just asking you if you have ever done or needed spatial aggregation in your research before, and ask you for some feedback on like what are, if you have, what are specific spatial aggregation needs that you might have. For example, I remember talking to Fabian and the pipe-side integration that they were saying, well, we always weigh our aggregation depending on nodal overall demand. This is a weight that we want to have factored in, and it would be really nice if you could take it. I think it's going to take 1 minute or so to like just say if you have ever done anything like this before, and what would be needs if you could write a list to Santa Claus or baby Jesus, as we have in Austria. In Austria, it's not Santa Claus that comes, it's the Christkind, which is essentially baby Jesus, bringing the presents. So if you could write a letter to Santa Claus or baby Jesus or whoever it is that you would write this letter to, Taylor Swift, then just write down what would be useful for you in a spatial aggregation setting, if you have ever used this, and then we can maybe in future research work on integrating this to see if we can make the package more useful for other people as well. So this was like just a very quick guide for you to have this Colab workbook and play with it if this is something that you want to do in your research. And now I'm going back here and I'm going to sum up this first part of the talk, but there will be more. You're like, oh my God, she's done. No, sorry, there will be a second part. So this first part concludes some of the theoretical results that we have had, and that computational complexity happens in optimization models because of time, because of space, because of technical things, because you have a lot of generators for different reasons, and that data aggregation can be very useful there. I have shown you a couple of examples where you see that exact data aggregation is possible, even if you have storage, even if you have a network, even if you have ramping, for example. And that in this setting, having a combination of data aggregation, but also disaggregation and separation of data into sub-problems that you can parallelize can be very powerful there. And that depending on the methods that you use, you can actually get error bounds on your aggregation. So we just had a discussion before with a colleague from the IT from Austria. I don't know where he is. He left. About like how do we do this in practice? And in practice, of course, you don't know the active constraint sets perfectly. So what we do in practice is we run an aggregated model and we get a lower bound. We get a projection, we get an upper bound. And the difference between these upper and lower bounds tells us something about the quality of the time series aggregation that we have done. So we can use this information to improve the time series aggregation that we have done, and then do another step or have an iterative procedure where we refine our time series aggregation until we have an optimality gap that we're happy with. Right, and then this idea can actually also be translated to space. Here I just talked about the data work here of the NPAP package. If you want to download it and use it, this would be super helpful. If you find some errors or you have some suggestions, then please don't hold back. If you want to give us a thumbs up in the package, we would also be super happy. But the most important thing is that this is actually useful to people. So this is the idea behind it. And the message to take home from this part of the talk is, and that's the most important thing for me, that the energy transition doesn't just need better models, it also needs better methods behind it. And maybe looking at very common methods from a different point of view can make them even more efficient and can make us get more bang for our buck. So this was the first part. And I'm going to, oh yeah, by the way, the papers are all online. There are a lot of papers of things that I have just crammed into a very short amount of time. So I would suggest if there are like some specific topics that you're most interested in, check out the paper, come and find me later on to discuss, because there is not enough time to go into every detail of every paper here, but it's on the website. Okay, so we continue. With this second part, where I'm going to be talking less and you're going to be doing more. My plan is, now I'm going to talk about one particular example of an optimization problem. So here, again, every detail of the optimization problem is not so important because I have coded this for you in another Colab workbook. But I still am going to go through the formulation in detail with you now so you really understand everything that's going on. So this is the full-scale optimization problem that we're going to look at now. And full scale here refers to full temporal resolution. Then we're going to look at different ways of aggregating, of having an aggregated optimization problem, that in the sense of aggregating time. I'll briefly talk about time series aggregation here. And then there is a challenge where you can get more chocolate. I think did you take some chocolate with you? It looks like some chocolate has disappeared. But in any case, the chocolate was supposed to be for the challenge, which I'm sure you will do anyways. And then we'll have the solution to the challenge, and I would then ask the challenge winners to come up to claim the last couple of chocolates that are still left. Okay? Good. So we're going into an investment problem. So now what we want to do is generation expansion planning. And for that, unfortunately, we need a couple of equations and definitions. So let's start with the definition of the sets, the indices. So again, G is generators. T here now is time periods in the full-scale model. So time. And let me start with the energy balance constraint here. So again, we have demand at time step t at every hour that we have to satisfy. And we satisfy this by production per time step and generator. This delta is just to, it's the duration of 1, because my power generation is in units of power, and this equation is in units of energy. So to convert my megawatt to megawatt hour, I have to multiply it by 1 hour, which is this delta. And then here I have my non-supplied energy. So I meet my power balance. And I have an upper bound on my production, which is my investment variable X. So X is the megawatts that I invest in generator G, multiplied by my capacity factor. And then I have non-negativity constraints of my production, my non-supplied energy, and my investment decision. And what I want to minimize is total system cost. So total system cost is investment cost and operating cost. Investment cost is my installed capacity X of G times my investment cost plus variable operating cost of my generators plus a cost of non-supplied energy should I have it. Very, very simple investment problem. Any questions here of like terminology, variables, parameters, anything unclear? Okay, good. So what I want to do here is now I will want to add storage to this problem, so we have something time blinking, because everything in here so far doesn't have storage, and I want to put storage in there. And so what we're going to add is a couple of variables that have to do with storage. So we also have installed storage capacity. We have charging and discharging of the storage technology, and we have the energy stored of at every time step. How does the power balance change? We just add the discharging and charging power of the battery. So discharging is like generation, and charging is like consumption. So this is why it has a minus. Then we have costs of charging and discharging in the objective function, costs of investment of the storage technology. We cannot charge or discharge more than the capacity that we have installed, and there is a discharge duration or energy to power ratio to go from the installed megawatts to the megawatt hour of battery storage capacity that we have available. And then we have this constraint, which we have already seen before in a different shape. So the energy stored at time step t plus 1 is the energy stored at time step t plus what I charge minus what I discharge. And these etas are just efficiencies. They are parameters that are telling me how much efficiency I lose in the charging and discharging process, and some non-negativity constraints. Up until now, yes or no? Yes? You're good? Okay. Right, so this was the full scale model. And now we want to have a time series aggregated model. And before we talk about how to formulate storage, we have to go a little bit into a philosophical question, is like, how do you represent time in a model like this? And depending on how you are going to choose to represent time, it's going to change how you are going to represent storage later on. There are different ways of doing this, and I have summarized the three main options of how you can reduce this temporal horizon. So I'm going to call the first one the load periods, or extended version of load periods. Then you could do chronological time steps in your model, or you could do representative periods, which could be representative days or representative weeks. Some of those have different names. Historically speaking, it could be load periods or time slices or system states or whatever. But these are the three main ways that you could go to do aggregated time representation. And depending on which one you pick, your storage formulation is going to look different. And we could fill another lecture just on how the different storage formulations would look, but we don't have that much time. So there is a way to formulate storage in all of those, and I've brought a couple of sources here. This is actually very hard, because as soon as you aggregate time and you have representative periods, you lose chronology. Right? So as soon as you build this, what I had before, this load period, this load duration curve, you have lost chronology among individual hours. But you need chronology to formulate storage. So what can you do? There are things you can do. It's a little bit messy. Sometimes it works, sometimes it does not. It has pros and cons. If you have chronological time periods, then this is very easy, because if you have chronological time periods, you still have chronology that you can build your storage state of charge equation on. This might work really well for long-term storage, but for short-term storage, this might be a little bit problematic. And you can do representative periods where you do have chronology within the representative period, but you have a little bit of a problem of what happens beyond the representative period. Because if you pick representative days, how are you going to formulate what a hydro reservoir is going to do? So for that, you can pick one of those examples, and there you then are going to have intra and inter-storage period constraints. This is a super interesting topic that we could talk about later on. So now what I'm going to do is I'm going to formulate two aggregated models. One assuming that I'm picking a time period representation where the time periods are all chronological. And then I'm going to pick another one where I have representative days and show you the difference in the formulation. Okay? So let's start with the chronological one. So here now my set of chronological time periods, representative time periods, is k. In the objective function, you will see that this weight of k is going to appear many times. So this is essentially how many hours of the original time series are represented by this representative period k. And this might not always be the same. So the first representative hour might be 10 hours, then maybe 20, then maybe 1. It depends, right? But this is this weight. Your energy balance constraint then, of course, depends on k, not on t. And you will have to, in your data aggregation, get averages, for example, of your demand for those representative periods. Same for your capacity factor. But apart from that, more or less everything looks the same than we had in the full-scale model. Any question here? Okay, so now let's get to storage, which is the interesting part. If we look at the energy storage dynamics, we have here k plus 1, we have here k. Since k is a chronological sequence, I can write this, and this makes sense here. The only thing I have to do is I have to multiply here with the weight of k, because this representative hour might happen 10 times in sequence. But apart from this, this looks very, very similar to the full-scale model. And then with this, I will not have to solve all of the 8,760, but just depending on how many hours you pick. Okay. Let's go the representative period way. So instead of having this chronological sequence, I have representative days that I pick. And I'm going to follow the Kotzur formulation that I mentioned before. So now in order to get this to work, I'm going to need a lot more indices. And I don't want you to get lost here, okay? Don't. Stay with me. It's not so, it's just a couple of new parameters and indices, but it's actually quite logical. So how does it work? First of all, I'm going to start with this index n, which is the actual days that I have in the year. So from 1 to 365. So I have first day of the year, January 1st, January 2nd, until December 21st. So this is an index with my actual real days in the year. Then I have my representative days, D. So there I might have less. Let's say I have 7 representative days. And then there will be a mapping with which of the actual days am I going to represent with this representative. So January 1st is representative 3. January 2nd is representative 2. January 3rd is again representative 3. So I make this list until December 31st, which is represented by representative day 1. So there is this mapping between the actual days and the representative days. This mapping I'm going to call f of n. And now within the representative days, we have our 24-hour sequence. And this is going to be, these representative time periods are. So here we have 24 hours for this representative day. And this means that what happens in day 3 and what happens in day n is going to be represented by the same variables. So all of the variables that depend on R and D are going to be the same for this first day and this third day. What's not going to be the same is the variables that depend on n, okay? Because for those, I have one for every different day. You see, it gets a little bit more complicated. So you just need a lot of time indices that are flying all over, really trying to represent the same thing that we said before. Okay, so our demand balance now depends on D and R. So I have a demand balance for every hour of every representative day. So if I have 7 representative days, I will have 7 times 24 constraints of the demand balance. That's a super good question. I would give you a chocolate for this, is just asking this question. So the question was, how do you decide the number of days that you need? And the answer is, you don't know. You really don't know. Most of the time, what people are doing is, how much can my computer take? So it dies, I can push it up to 12, and then my computer dies, so 12. We will ask Jenny how they pick 12. I bet maybe it was like this. So usually you try and pick the maximum that you can in a computational time that's reasonable to you. But this is, of course, something that you don't know. You don't know how many representative days are good enough, because a lot of times when you solve these aggregated models, you don't know how far away you are from the truth. This kind of ties to my talk before, where if you have a method where you can actually get such an optimality gap, then you could say, well, I have run this with 300 representative periods, and I have a 2% gap. That's good enough for me. But maybe 200 are very bad. So, but then at least you would know. In practice, usually how it works is, depending on your favorite clustering algorithm, you would maybe pick 5, and then, or start with 1, 2, 3, 4, 5, 6, or whatever, and then you would run your aggregated model and see how your objective function behaves. And if you have maybe some kind of elbow curve behavior where you see, so if I pick 7 or 8, the objective function doesn't really change much anymore, so then I will pick 7, because then it seems that I have converged. But this is, of course, all hand-wavy, right? So we pick and hope for the best. I don't know if somebody else wants to share their own story, like this is how I picked 7 or 12 or whatever, but a lot of times this is how it goes. Does this answer your question?
Yeah. I have another following question.
Yes?
Besides these numerical studies to see that maybe it will not reduce anymore, okay, this elbow what is the number of representative days that I will choose.
Mm-hmm.
You also mentioned in your last section about the performance error bounds.
Mm-hmm.
This number of representative days will also impact your performance bound.
Yes. Usually, if you do your job right, the more representative periods you pick, the tighter your bounds are going to get.
Is the more the better?
If you do it right, then yes. But if, for example, for your a priori method, so if you're just going to look at the data and you're going to do k-means, usually the better it gets, but it doesn't have to be a monotonic behavior. So it could actually happen out of chance that with more clusters you do a worse job than before. If you think of the example with the 3 clusters that we had, they're really just going to depend where your centroid is going to land. And if your centroid falls into a place where you have, for example, non-supplied energy, you're going to say, I have this many hours of non-supplied energy and that many hours of thermal generation. And on average, that might be closer than if you pick centroids a little bit further away. But this is completely random, actually. So in general, you see a trend. The more representative periods, the better you get. Because, of course, if you pick 8,760, you get a perfect answer. But it doesn't have to be monotonically increasing. With the performance guarantees that we do, of course, since you have this check, you can, of course, guarantee some kind of monotonic, non-increasing behavior. But if you're still very far away, then that just doesn't help you at all either, right? Yeah, thanks. Okay, so here, instead of having just k, we have these representative days and the hours within the representative days. Everything else is more or less the same. So now you're going to ask me, where does this n come from? We need this for storage. So if we go and look at how storage is done, so far so good. We just add discharging and charging to the balance constraint. And now let's look at this. Please don't look at the millions equations and just shut off. It's actually not that difficult. So you have representative days. So within the representative day, you have chronology. So you have 24 hours that are chronological to each other. And this you're going to use here. Okay? So this up here is called the intra-day state of charge constraint. So within this day, you have chronology that you can use. So here, what you do actually is not sum up or not have the state of charge, but the accumulated difference in state of charge. So this delta E is the accumulated difference of state of charge over the course of this day. So in the first hour, you have nothing, and then in the second hour, you have whatever you had accumulated in the first hour plus what you charged and what you discharged. So there you accumulate the difference in state of charge over this day. And then here, you establish chronology between days. Because, of course, if you have long-term energy storage, you cannot see what the hydro reservoir is going to do in just 24 hours. It's not going to work. Also, a hydro reservoir in January versus in June is not going to do the same thing. The state of charge will be different. Even though hydro inflows and demand for those 2 days might be exactly the same, your hydro reservoir is going to have a different state of charge because it has memory. It has discharged over time, right? So this is why your actual state of charge cannot depend on the representative day. It has to depend on this other index here. So what you're doing is, okay, so my actual state of charge in this particular day, n+1, was what I had the previous day, plus, and this variable is essentially just this delta from up here, plus all of the accumulated delta I had over this representative day, more or less. Okay, so you don't have to be able to recite this by heart at lunch later. I just want you to get a little bit of the feeling for why people have been doing this, and I would say these types of approaches right now are the state of the art of storage modeling in long-term problems. There are slightly different approaches, but this intra and inter storage dynamics kind of helps you to capture short and long-term stuff. So I would say more or less this is what people have been using, even though so far we haven't gotten any performance guarantees on this yet. We have been looking at it, but we only have performance guarantees for the chronological periods. Okay, so you have seen this plot. We have time series data of capacity factors of wind and demand. And then you do whatever it is that you do. And the terminology that I want to frame here now is time series aggregation creates a mapping. So it creates a link between the actual hour that you had in the year and a representative hour that you're going to use in an aggregated model. So for example, for this 5 representative hour example with k-means, the mapping would look like this. So hour 1 is cluster red, hour 2 is cluster red, hour 37 is cluster green, and so on and so forth. So this mapping is establishing a link between actual hours in the original time series and representative hours. And this is going to be important later on. Okay, so k-means, I think everybody knows what. Does anybody not know what k-means is? No, okay, good. So k-means, you can use it to get representative hours or days or weeks. And this can be very useful in data analysis. Be careful if you have representative days, what happens beyond the day if you have long-term dynamics in your system. How could we, if we have this chronological model, how could we use k-means and get a chronological time series out of this? So imagine you do k-means and you say 3 clusters. This is what you get. You get a mapping here, and now what I would like to have is actually a chronological time series to use in my first aggregated model. So what could you do? You could say, okay, I take this mapping that I got, and now what I will do is, if in consecutive hours I'm in the same cluster, those I will just aggregate. Okay? So if my sequence was red, 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 orange, 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 then I would make these first 7 hours one cluster, and then the next 10 hours one cluster, and so on and so forth. Okay? So I will just go through this mapping, and wherever I have consecutive hours that are in the same cluster, put them together. This is a priori for now. This is just looking at data. And then I would get the chronological sequence of 720 time periods. This is a little bit problematic if I have a limit of representative periods that I could use, then, but in any case, this is 720. You could do hierarchical clustering. This is the code of a very nice paper of Salva and Juanmi, where essentially they look at the data and say, look at the 2 consecutive hours that are closest to each other in data and aggregate those. And then do this iteratively until you arrive at the number of clusters that you have. And then you get a chronological time series out of this. Okay, so now with this being said, we come to the challenge. Does anybody not know what movie this is from? You are very young, so it might happen. I don't know. So this is from Star Wars, the original series, which is a great movie, and you should definitely watch if you have time. Let's try and see if this time, if you go to this Colab notebook, it actually works. Otherwise, we will need John to rescue us again. Thanks a lot for doing that, by the way. So on this next Colab notebook, what I have is, actually I have coded an optimization problem. And by I mean Jakub did it. So there I have, I will show you in just a bit, the full optimization problem that we have just seen. I have the 2 aggregated optimization problems that we have just seen, where you have either chronological time periods or representative days. I have a couple of examples of clustering methods there that you can use. And now what we will see is how good they actually are. Okay? So let's go to this notebook. If again you could create a copy for that would be good. And we have more or less 50 minutes to do this, so I think this will be enough time. Okay, so I again go to run all. Okay, so in here, just for you to have an overview, we have 7 sections. In 7 is where you have the challenge and you have to code something, okay? So in 1, this is just the environment that's going to be configured. In 2, you will see the data that we are going to load for the problem. In 3, there is the full-scale optimization problem that we have just seen on the slides. It's exactly the same. And then on 4, we have a couple of time series aggregation methods that we can then plug into the models in 5, which are also exactly the same as we have just done. Okay, so setting up the model, we have 8,736 chronological hours, because that's a multiple of weeks. So this is why it's not 8,760. I have a wind generator, a thermal generator, and non-supplied energy with variable costs of 360 and 5,000. These are the efficiency values that we have, the investment values that we have. Then we have time series data, which is the capacity factor for wind and the demand, exactly as we had in the model formulation. And this is just some graphical representation of the input data if you wanted to see the distributions, but the data is all there for you to look at if you want. This is the full-scale optimization model that we have already seen, right? So we have investment variables and operational variables. So investment is X, operation is P. We have our storage dynamics, upper and lower bounds. So this is the model. Then here in the part of time series aggregation, there are some methods coded for you. So the first one here is a k-means, where just like it was on the slide, I pick representative hours, and then I kind of chronologize what I get. I chronologize the mapping to get a chronological mapping out of this, where I have the 720 chronological time periods then later on. I can use k-means to get representative days as well. And really, I mean, it's just whatever you put into k-means. If it's a vector, you will get representative hours. If it's a matrix with 24 columns, you will get representative days, whatever you want. And then down here is this chronological hierarchical clustering that Salva and Juanmi came up with, where you take the full time series data and you iteratively reduce it so you get a consecutive time series. This is the code for the k-means clustering. You already saw this. This was the time series, and this is the chronological sequence. So this is the mapping that you get, right? So I mentioned that this mapping was what I was after. This mapping is going to be important because this is what you will need for the challenge. You will need to submit a mapping of the original hours to your representative periods. If you do the hierarchical chronological clustering, you also get a mapping. This is what it looks like as an example for you to see the difference. This is the representative day clustering, and there you also get a different mapping for you to check out. Then in 5, it's the aggregated models you have already seen. You don't need to change the code of these models at all, actually. So this first part is the model where you have chronological periods. And the second part is where you have representative hours. Right, this is the Kotsua model that you have already seen as well. Okay, and then now the question is, how do I evaluate this? Okay, because what I want to do is, I want to take the time series aggregation, the mapping that I have gotten, and I want to know the difference between the full-scale model and this aggregated model. Okay, so if you do this here, you can evaluate your mapping. And then you will get a different plot and a comparison between the full-scale model, because here we know the full-scale model. We have solved it, and we see the difference between the investment decision of the full-scale model and the K-means model that we got with 720 periods. With the chronological, so here with the with this we get an error of 1.26% in the objective function, so that's already pretty good. Then here with the chronological clustering you get an error that's even smaller, so 0.87. And with the representative day Kotsua model you get a 3.26 with, I think we picked 30 representative days, so it's more or less the same number. And now what I would like you to do is I would like you guys to come up with your own mapping. I would like you to aggregate the data and play with this so you find your own mapping, and the only limitation that you have is it cannot have more than 5 representative time periods, so just 500 steps. And once you have created your mapping, then here you can evaluate it. So you just essentially have to plug your mapping into this piece of code. And then what it will give you back is an error message if it has more than 500 time periods, for example, which is what happened here right now. I just plugged in the mapping from K-means that I got. But it also gives you a relative error. Okay, so in this relative error is the number that then you have to submit in the coding challenge. Okay, so what you have now is, let's say, half an hour. You can do this in groups. You can do this by yourself. You can go through this. You can change anything you want. Ignore challenge 7.2. I was super ambitious in terms of like what I thought we would get done. I don't think we will do it. Create your own mapping, and once you have the error that it gives you, you can submit it at this form. Okay, so here you say, okay, so my first name is Sonja, my last name is Wogrin, and I got a 1 point, or let's do something bigger, 2,000 whatever %, even though that's not it. Then I submit this. And then I will have an online live ranking of like who is currently leading the board. So even submitting things that are already in the Colab notebook is already valid. One very simple thing that I would ask everybody to try is if you go to this chronological hierarchical thing, there you can just say make this 500. Get a mapping and submit the mapping here. So then this will for sure be less than 500, and that one was already pretty good, so this will be like less than 1% error already. So I think this is something that everybody can try. But of course, if you have better ideas with what you have learned from today, from the first part of the lecture, please go ahead and submit all of the very great mapping ideas that you could have. So let's say half an hour, and then we will see how the leaderboard looks like. And then I will ask the challenge leaders to come up and claim their wonderful chocolatey prize. Yay! Everybody should try to submit at least once. I think that would be good. So the best one is still 0.88 for now. But 4.1 is also good. 0 is possible. And in this particular problem, I mean, I'm allowing you to cheat, right? You have the full model solution. You can use the full model solution if you want to look into model outputs. In challenge 2, I would not have allowed you to use it, but here, you can look into the full model solution and see if maybe with this you can figure out a better mapping even than the one that you have. This is looking very, very good. So I would say we stop the challenge here. Unless you need to submit something very fast, then still do it. But if not, then I would ask the first 10 people to come out and collect their applause and their chocolate for having done a really, really, really brilliant job in this very short amount of time. So Gayur, Disha, Andreas, Anda, Gloria, Juliette, Valentin, Ginevra, Luis, and Jenny, please come out to collect your chocolate. And if you don't mind, stay here for a picture. So you are number 1, then Disha, number 2. Congratulations. Then we have Andreas. Anda. No, that's you. Here you go. Gloria, I know. Juliette. Valentin, here you go. Ginevra is here. And now for the other ones, I have cookies. Luis, here you go. And Jenny. Who have I forgotten? Oh, Kara, where's Kara? Kara? Well, but we have one more, so that's good. Come out, Kara, do it. Come on. You can share, there are like 10 in there. Okay. So I think you guys did a wonderful job. It's like I threw a lot of content at you. Come here, you guys. Center stage. Applause for the really great challenges that you did. Thanks a lot. It's very, very hard to do this in this short amount of time and under this pressure and all of the content that I see cucumbered at you here. So this was very impressive. And now I will take, I still have 7 minutes, Jalal. Yes. I will need them, sorry. I will need them just to give you a little bit of the solution. So this is why you don't have the slides yet, because there was the solution to this on it. So you could actually get this to 0 if you were looking into the dual variables. So Gayur already spoilered this a little bit. So essentially what you can do is if you look at one particular set of dual variables, which is the marginal costs. So the marginal costs give you a very, very good information about who is the marginal operator because of the variable costs. If you were to plot all of the hours of the full model according to their marginal costs, then this is what you would see. You would see only 10 different values. And if you then group the consecutive time steps with the same marginal costs together, you would get 409 consecutive time steps, which is less than 500. And then with those, you should get an error of 0 to the challenge. So where do these numbers come from? It depends on the marginal operator, or whether this is actually an hour that's like an operating state, or whether it's an investment state. So there you also have investment costs in there. And I will upload a Colab workbook where there is a full solution to this as well. Why does this work? It's math. Math is great, and so are cats. And essentially, you can prove that if you take averages over time steps that have the same simplex basis, then you don't incur an error. So this is very nice. How to do this in practice? Actually, with iterative methods, you can come close with the bounded error. I didn't talk about this today here. We didn't have time for the second challenge. But if you're curious, there is another challenge, 7.2, where you're actually supposed to code an iterative method that doesn't use the full model solution to come up with this. And this is just to compare the difference of if you had used different mappings with different aggregated models, you would get a different error in different things. And it's quite random sometimes. So 5% error in the objective function might not look like it's a lot, but if you look at storage investment, for example, this is really bad. It's 85%. So sometimes it translates really, really badly. This was the challenge to the second part. There you could do some iterative things if you didn't solve the full-scale model, and you could do a lot of fun iterations, but this will be for another time. Another challenge. And so with this, I want to close again. I hope you had a little bit of fun today. For sure, you got a lot of chocolate and a lot of input. I had great fun. I thought it was super impressive what all of you did in this very short amount of time and how low you could drive the error. And I'm looking forward to a lot more fruitful discussions in the next couple of days, and would be very happy to see any one of you visiting us in Graz at any time. So for more chocolate and Mannerschnitten. So thanks a lot for the attention.
Any final question to Sonja, if you have any final question?
Can I just say, I stayed in Spain for 10 years, and I'm so punctual today that I'm even surprised at myself that I made it on time.
Cool. Thank you so much, Sonja, for a very nice presentation, nice challenge.
Thanks a lot.
Also, congratulations to the first 10 and all of you participating in this challenge. Thanks.
Perfect. So see you guys at lunch.
Thank
Thanks.
you.